Okay, this video here is on the precise definition of a limit. So we're going to be talking about the same thing we've been talking about, just in more exact terms. And so the main goal here is we're going to go back and talk about this statement. So the limit of the function as x approaches a is equal to L. And we know informally what this means is that as we let x approach a, the function values, right, the y values will get closer and closer to L. So the words like approaching and getting closer to and very near to, the expressions like that, what we're going to try to do in this lesson is to make those words more precise. So just as some background, because the definition is pretty challenging, we're going to use these notations here, epsilon, and also delta. So these are letters of the Greek alphabet. So we're going to use epsilon and delta to indicate very, very, very small positive numbers. So once we see that, we can start talking about the definition. So here it is, and like I warned you, it's tough to understand this the first time. So this definition says, right, remember these are small positive numbers, so if we are given epsilon to be positive, a very small number, then the definition says that it's possible for us to find a delta value, right, a corresponding small number, such that if this first statement occurs, x minus a in absolute value is less than delta, then that means what follows is the function value minus the limit, right, in absolute value is less than epsilon. So what this is telling us in plain terms is that we have two very small numbers that are interacting. And if we are given a small number, epsilon, then that means the definition says we can find another number that corresponds to it, so that if x is taken really, really close to a, because notice when you subtract x and a, there's almost nothing there, right? It's less than delta. Then that means if you look at the function minus the limit and you subtract those, that is less than epsilon. So one way of translating this, right, you can translate this statement, right, to mean that x is within delta units of a. And what that means is x is really, really close to a. And then if you look at the second statement, very similar, right, the function is within epsilon units of L. And again, that makes sense with talking about getting very, very close or approaching these numbers. So what I would like to do with this definition is to just take a look at a diagram. I think this will help solidify what it means. So I'm just going to draw a plain old picture here. We'll call this F. And down here we'll have A. And over here we'll have L. Okay, so to get a handle on what this definition means, right, epsilon is given in the problem. So we're going to surround the limit value with a small little window here. So this is L plus epsilon, L minus epsilon. So epsilon is really small, we just have a small window surrounding L. So according to this definition, we can find another value, delta, right, and that's going to surround the A here. So I'm going to go down and find the function and create a small window here, just like this. And so it says that if you take x very, very close to a, right, within delta units of it, so you can make a little window here. So we can call this a minus delta and a plus delta, like this. And then what the definition is saying is you can take any number, right, in this little band, right, in this strip here. So if you take any point here, then you're guaranteed to fall within the band on the y-axis. So you can take this value here and follow it over here, and you will fall within this band. So the thing that's tough about this definition is that the epsilon is given. You have to find the delta, right? But then the delta value is the one that you're using, right, on the x value to map it to the values on the y-axis. And the other thing that makes this challenging is once you find a delta value, if you're given another epsilon value, most likely the delta value that will work for that one will be different, right? Because these two numbers are corresponding numbers, they're connected. So once epsilon is given, delta often depends on it. So what I'd like to do here is just to look at a couple of simple examples of this, just to make this a bit more concrete. Okay, so we'll take a statement that is pretty easy to grasp here, something like this. So we know that if we take x really close to 3, the function 2x plus 1 will get very, very close to 7. So we can try the definition here to see if this is going to work. So we're going to say, suppose we have epsilon equal to a very small positive number, right, 0.01. Then the question we would ask here is, what would the delta value be, right? So we're going to see if we can try to figure that out. So I'm going to write down the basics of the definition here so we can see this. So this is the first part here, taking x and a really, really close, and then we end up with function minus limit being very small. Okay, so this is provided for us, right? Epsilon is equal to 1/100th. And you can tell in the context of this example, this is our f, right? This is our function, this is our limit, L, and then this is our a value, right? A is equal to 3. So what we try to do here is to play around maybe with this inequality and see if it at all connects with the original one, because most likely the epsilon and the delta are related in some way. So I'm going to take this statement here, just play around with it a little bit, right, by using the information that we have here. So it would look like the function minus the limit, right, and this is going to be less than 0.01. Right, because this is provided in the problem. Okay, so we can probably get rid of this here. Okay, and we're going to try to simplify this a little bit. You can see this is going to be 2x minus 6, still an absolute value less than 0.01. And so I'll continue this up here to see what we can do. Okay, you can factor out the 2. So it has this form. And then notice now you can take the absolute value of each component here. So this will just give you absolute value of 2, better known as 2. And absolute x minus 3 is equal to this here. And then now what you can start to see is that this inequality is connected to this one. So if you think of what this inequality means in the context of this problem, right, this one takes the form of x minus 3 being less than delta. So if you look at this inequality that we have here, and this was a result of playing around with this one, it has a very similar structure to the original part. Okay, so we can connect these two just by dividing both sides by 2 here. So here we have absolute value of x minus 3 is less than 0.01 divided by 2. And then I think this is the place where now you can look at these inequalities, and I'll put an asterisk on each one. This statement here, and then also this one here. So you can see we have absolute x minus 3 in 2 locations, and so that is suggesting that this could be your delta. So you can see it's sitting in the same spot as that one there. So when we say epsilon is given, right, to be a certain number, and in this case epsilon was 0.01, then we would say, what is our delta value going to be? Well, this is one that is suitable, right? 0.01 divided by 2. So we could say in this problem, this would be a delta value that would be acceptable, right? So delta is equal to 0.05. So notice when you think about the definition, this is a boundary value of delta. So this is the largest value of delta that would work, but you could also pick something like 0.002, right? That would also work because that would still allow the values along the x-axis to fall within the small strip L minus epsilon, L plus epsilon on the y-axis. So that's really the way that that works. Okay, And again, the reason this is challenging is because this just indicates that if you pick epsilon equal to 0.01, there's a corresponding delta that you can find that's going to work. In this case, you can tell by the relationship 0.01 divided by 2, that will always be your delta value. So if someone challenges you with the same type of thing, saying this, right, well, now let's change the epsilon value to something even smaller, right, 0.0002, and then you could ask yourself, what is a suitable delta value? You can think about it in terms of what we did earlier, right, taking the epsilon value and then dividing it by 2. And once we understand it that way, it's pretty straightforward to come up with the delta. So you can see the dynamic here that once this is given to you, this corresponds to it, right? So you can find a delta value that will satisfy that definition. Okay, so the last thing I would like to do here is to actually prove this mathematically so we can see what this looks like. So I'm going to come back to the statement. So the limit as x approaches 3 of 2x plus 1 is equal to 7. So what we're going to do is to actually prove this statement and see if we can go through a more general argument than what we were talking about in the last little exercise. So what I'm going to do here first is to write down just the basic statement so we can see what we have to prove. Remember that epsilon is greater than 0. This is given to you in the problem. And what we have to do is to find a delta that will work. So find a suitable delta. Right, that's what we have to do. And so we should write the inequalities down so we can see what is happening in the statement. So I'm going to write down the general form first, like this. So we want to start off with this and show that function minus limit is less than epsilon. Okay, so a big reason these are tough is you have to separate assumption from what you have to prove. So this is what we can assume in the problem, this is what we can use, and this is what you need to show. So this is what you have to prove. So you have to prove this. And again, you can see all the pieces in this problem that your f of x is 2x plus 1, your a is 3, and your L is equal to 7. So you can insert that information in the statement and then think about the logic and the direction that you have to move in. Okay, so I'll keep this statement down here and then I'll import the correct information into that statement. Okay, so for this problem, it's going to look like this. Okay, because we're approaching 3. So this will be the assumption here. And what we'll have to show is that the function minus the limit, so 2x plus 1 minus 7, this is going to be less than epsilon. So we have to show this statement by using this information. So I'm going to remind myself of that right here. So you need to show that. Okay, so let's write down the proof. This is what it's going to look like. Okay, so epsilon is greater than 0. This is given. Okay, and now what we're going to do is to choose the delta based on the scratch work and the little bit of work that we did on the other problem. So epsilon is greater than 0 is given, so we're going to let delta equal epsilon over 2. And the reason for this, right, is based on what we did in the earlier exercise. So for example, if we look back at some of our values, when we were given this to be the epsilon value, what we ended up finding was that this is the delta value that will work, right? The largest delta value that corresponds to it. And you'll notice if you cut this in half, you're going to get that. Okay, so we're going to let delta equal epsilon over 2, and then that's it. We're going to try to prove this statement. The reason this is difficult to prove, right, if you look at this statement, it's a difficult one to show because you're not trying to show that something equals something else. You're trying to show that something is in fact less than something else. So the best way to do that is to not really write down the statement, but to write down part of it, right? And then to see if eventually you can get this to be less than epsilon. So I'm going to start off with the left-hand side of this inequality. So I'm going to write absolute value 2x plus 1 minus 7. And I'm just going to leave it at that, right? Just leave it in that form. And then from our earlier work, we know that this ends up being 2x minus 6. Right? So this is the absolute value, 2x minus 6 like that. And then we can pull out the 2, right? And then bring that out of the absolute value. So I'm going to just write it this way here. Okay, now this is where the stuff gets pretty important. So we now have 2 times the absolute value of x minus 3. But remember, as we mentioned earlier, this is the part that you can assume in this problem. So anytime you encounter the absolute value of x minus 3, you can say that it's less than delta. So here we have 2 times the absolute value of x minus 3. So this statement here, we could say this is going to be less than 2 times delta. So all we're saying is absolute value of x minus 3 is less than delta. So 2 times the absolute value of x minus 3 is less than 2 delta. So this here we can say is true by the assumption. Okay, and as we keep plugging here, now you can say, well, delta here, we let delta equal epsilon over 2. Right? So this is something that we chose based on the earlier work. So what we're going to do is to put epsilon over 2 in place of delta. Put it in right there. And then notice the 2's conveniently cancel out and you end up with epsilon. Okay? So this is, like I said, it's a tough little exercise, but if you look at what we have just shown, you'll notice if you step back from what's written in red, this part right here says function minus limit, right? And then if you look down the line, absolute value of function minus limit is less than, right, epsilon. So that's exactly what we needed to show right here. You can see f of x minus L is less than epsilon. So we have that string of inequalities here. And notice that that is only based on choosing a delta value that you know is going to work, and then using your assumption that x minus a is less than delta. So this is really what the mathematical proof, right, of saying the limit as x approaches 3 of 2x plus 1 is equal to 7. This is how you would actually prove that statement.